Did I do it right?
Yeah. So I think there's issues with the homework 0. I want to see the file, but like it seems like it doesn't fix.
Okay, ask me after class, I'll fix it.
Yeah.
It's not on team.
No.
Okay, I'll fix it after class, not now. Okay, so let's get started then. Last time we looked at renormalization group transformations, and we introduced the idea of linearizing the renormalization group transformation near a critical fixed point. So I've drawn that schematically here in the middle of the page on the right, and also on the left too. So what we did was we said, well, the renormalization group transformation takes a vector of coupling constants, could be an infinite vector for all we know, and does some transformation after you've done the coarse graining. In general, you're going to get some huge big mess, very difficult to calculate. Never mind that, let's just see what will happen if you look at that near the critical fixed point. So we were putting aside the question of how do you do the calculation, and we're just saying, let's suppose we somehow figure out a way to do it. Then let's ask, what is the outcome? So we look at the critical fixed point, we call that K star, we linearize around that. So you have delta K, which is how far away you are from the critical fixed point with your particular physical system that you're looking at. And then what you do is you ask, how does it transform under a renormalization group transformation? And the answer is it's going to be some linear term, depending on how far away you were from the critical fixed point, then plus higher orders in delta K. So in general, we can say then that this is a matrix M, some matrix that we have to determine, and then there'll be higher order terms in the deviations away from the critical fixed points. And we know it should be linear like this because we know that if you are at the critical fixed point and you do a renormalization group transformation, by definition, you stay there. And so therefore, the flow, when you're slightly away from it, is going to be small, or should be small compared to the distance you are away from the critical fixed point. And I wrote it out in component notation at the bottom of the page there, where the matrix elements are simply the derivative, whatever is the renormalization group transformation, evaluated at that critical fixed point. Now, we ended last lecture with a note of caution that in general, the matrix is not a symmetric matrix, so the eigenvectors are not orthogonal, the eigenvalues are not necessarily real, and you get left and right eigenvectors, and I'm going to now explain that to you. So it's not going to be exactly the same as what you're used to in quantum mechanics, but it's not that different. So let me talk about what I mean by right and left eigenvectors. So in quantum mechanics, you've run across this actually. You might have some operator, some Hermitian operator, it acts on a ket, or it might act in the opposite direction on a bra, and so you can write eigenvalue and problems, eigenproblems, both going backwards into the dual space and forwards into the regular space. So here we do the same thing. We've got a matrix M. The right eigenvalue is as you take you take some vector which you have to find, and then you demand that the M acting on that is proportional to that vector, and lambda is the eigenvalue. And then in general, there'll be many eigenvalues, so we label them by the number sigma. So that's called the right eigenproblem. The left eigenproblem is where we have the vector E acting on on the left of the matrix M, and so that produces the vector E multiplied by some different value lambda left of sigma prime, and so that's the general situation for a matrix which is not symmetric. But in fact, these eigenvectors do have an interesting property. So again, sigma and sigma prime just label the eigenvectors, the right or left eigenvectors. So I'm going to show you now that the left eigenvectors are orthogonal to the right eigenvectors. And how do we do that? Well, take the equations 1 and 2 in the middle of the page, the right and the left one. Take the one equation and multiply it on the left by E left, sigma prime. That produces E sigma prime, so E left times the matrix M times the vector E right. And then if I take the second equation, I multiply it on the right, excuse me, I multiply it on the right by the right eigenvector, I also get this object, this bilinear object with a E left dotted with the M dotted with E right. And but on the right-hand side, I get different objects. On the right-hand side, if I subtract those two equations, then what I get is that E sigma prime dotted with E sigma on the right times lambda sigma minus lambda sigma prime is equal to 0. So because the left-hand side of doing those operations on each of those equations gives me the same object, E left transpose times M times E right. And so that must be equal to 0 when I subtract it. And assuming that the eigenvectors, so assuming that the eigenvalues are non-degenerate, then the lambda sigma is not equal to lambda sigma prime. And so therefore we have that the dot product of the left and the right eigenvectors has to be 0. And it can be more complicated than this, and that's discussed in section 9.4.4 of my book. So that's the situation. Now, what I want to do next is I want to proceed by assuming, just for simplicity, that the matrix M is symmetric. It's not, but it's easy to generalize the formalism. So now I want to show you some new results. So the next thing I'm going to show you is so the next thing we're going to do is we're going to derive Kadanoff's assumption number 2. Kadanoff's assumption number 2 was that if I say, I ask how does the reduced temperature scale with the coarse graining size L, what he assumed without any justification other than it looked like it was going to give the right result, which it did, he just assumed that T sub L goes like T times L to the Y sub T. And now I want to show you where that comes from. So let's go. Let's see how this actually works. So what we're going to look at is the eigenproblem for our matrix M. And our matrix M describes a renormalization group transformation of scale L. So M will also have some dependence on L. So I can write this as M L acting on some eigenvector E is some lambda times E. But because the matrix M depends on L, therefore we expect that the eigenvector, so the eigenvalues, will depend on L. And in general, of course, there'll be many eigenvalues. So I will label those by the label sigma. Now, what we're going to do is we're going to use the semigroup property of the renormalization group transformation. So what was the semigroup property? Well, remember what we do is we start off with a system with some set of coupling constants K, and then we do a renormalization group transformation up to scale L1. And then let's suppose we say, well, that's great. Now we've done that. Now let's do another renormalization group transformation up to a scale L2. And what that's going to end up doing is going to be as if we had just taken our initial vector of coupling constants and done a renormalization group transformation by the amount L1 times L2. So that's what I call the semigroup property. It just says I scale by L1, then I scale by L2, I've scaled by L1 times L2. Okay, so now if I then now plug this in the semigroup property is now shared by the linearized renormalization group transformation. So this is going to be shared by our matrix M, our linearized renormalization group transformation. And so what that means then, just reading it off here, is that M of L times M of L prime is equal to M of L times L prime. And once I have that, now then I use the eigenvalue problem. So because each of these matrices satisfies this eigenproblem over here, then what that implies then is lambda L of sigma, lambda L prime of sigma is equal to lambda of L prime sigma. Okay, so that's just from the eigenproblem. Okay, so what I'm going to, so now we have an interesting question, because this lambda L, this is really just some function of L. And so you might ask, what functions would obey this semi-group equation? And you might say, well, that's an interesting question. How do you solve functional problems? You're used to solving algebraic problems. You're used to solving problems in calculus. But here we've got a problem where I'm saying, here's some general formula. And I want to find what is the set of functions which can actually do this. It's not obvious that anyone can. And you might say, well, there's probably lots of them. But in fact, there's only one. And now we're going to see that. So the answer to the question is that lambda L of sigma is equal to L to the power of some number, which I'm going to call y sub sigma. And that, of course, is the root of the Kadanoff assumption number 2. So that's the answer. So how did I get that? So let me show you a neat way that one can do this calculation. So the first thing I'm going to do is in this equation here, in this semi-group equation, what I'm going to do is I'm going to first of all set L prime equal to 1 in the semi-group equation, in equation star. So if I do that, then what I get is lambda L of sigma, lambda 1 of sigma is equal to lambda L of sigma. Okay, so that then tells me that either the lambda is all 0, which is not the case, or that lambda 1 of sigma is equal to 1. So when L is equal to 1, when I've done actually no coarse graining whatsoever, the eigenvalues are just 1. So that's a kind of boundary condition. So that's step 1. Okay, can anybody see how you might do step 2? What you might do next?
L prime is 1 over L.
Okay, so you're thinking, okay, one of the ways that we solve these problems is we say that since it's true for all L, we can just choose different specific values. Yeah, so good thinking. But I don't think so, because well, I'm not saying you're wrong, because I can't think it through so quickly live. But what I'm going to show you is the way I did it, is I figured out a differential equation that this function satisfies. So let me show you how to do that. So step 2 is derive a differential equation for lambda of L. So what I'm going to do is I'm going to take the so the idea is take the semi-group equation, take star, and I'm going to differentiate it with respect to L prime. So I've got lambda L, lambda I'm not writing down all the sigmas just to save time. So I've got this is equal to d by d L prime of lambda of L prime. That's what the semigroup equation says, just by differentiating it. So I can then say that, well, so lambda of L times d lambda L prime by d lambda by d L prime, that is equal to, and I'm going to use the chain rule, d by d L prime of lambda L prime times d L prime by d L prime. And then that is just equal to d lambda L prime by d L prime times the factor L that I get from the chain rule. Okay, so now what I'm going to do is I'm going to say, well, what does this equal? Well, so I can set lambda equal to 1. So it's not lambda, so L prime equal to 1. So again, set L prime equal to 1. So now what I get then is that, I wish I wasn't colorblind. So now what I will get is lambda L times d lambda L prime by d L prime evaluated at L prime equals 1. And then that equals, well, if L prime is equal to 1, then this is d lambda L by dl, and then it's multiplied by L. Okay, now this thing over here, this thing is this derivative evaluated at L prime equals 1, so it's just a number, 17 or something like that. So I'm going to call that number, because I know what I'm going to get, I'm going to call that number y sub sigma, okay, some number. Why are you laughing? I mean, I could have called it hippopotamus, but in the end, it would end up being y sigma. So I'll call that number y sigma. It's just a number. So now I've got the differential. I've now got the differential equation d lambda L by d lambda L divided by lambda L, and I'm going to put in the sigmas. And that is equal to y sigma times dl by d over L. So that's a differential equation that even a tenured professor can solve. And so then that gives me that log of lambda L is equal to y sigma log of L. And so lambda L of sigma is equal to L y sigma. And if L is equal to 1, then this thing satisfies our boundary condition that lambda 1 of sigma is equal to 1. So this is the solution of this equation. And so that's that is the basically, as we'll see, the reason why Kadanoff's assumption was the correct assumption. So the important point to note in everything that I just showed you, this number y sub sigma is just a pure number like 13 or 17 or 137 or something. So this is independent of L. And the fact that it's independent on L is going to end up being one of the reasons why we get universality. Okay, so that's the semigroup property. Okay, so the next question we want to ask is, now that we've understood the eigenproblem has very specific solutions. Now we want to ask, if I take my vector of displacement away from the critical fixed point, how does it transform under M? And so the strategy that we're going to employ is we're going to do an eigenvector expansion. And I'm going to do it not differentiating between right and left. So I'm just going to do it pretending that everything's symmetric and they're the same, but you can completely easily generalize this. So what we're going to say is that, well, I've got my vector delta k, that's where I start. I'm going to write it down as a sum over eigenvectors. Those eigenvectors are labeled by sigma, so therefore there should be some expansion coefficients A. Those expansion coefficients will be associated with each of the vectors, the eigenvectors, so they're labeled by A sigma. And if I want to know what A sigma is, I am going to assume that everything is symmetric, so I can just take the dot product with delta k, and so A sigma is just the dot product of E sigma delta k like that. So just like you do in the expansion method in quantum mechanics, we do that. Okay, so that's that. So now when we compute what is delta k prime, well, that is going to be M, the matrix M, acting on delta k, and the matrix delta k now has an eigenfunction expansion. So this is the matrix M acting on the sum over eigen vectors E sigma, and then because the E's are the eigenvalues, the eigenvectors, I should say, then that's going to give us the sum over sigma of A sigma lambda of sigma times E of sigma. And so we can think of this term here as being the expansion coefficients for delta k prime. So this we can write as A of sigma prime. Okay, so let's have a look at what those expansion coefficients look like. So A sigma for some particular direction sigma now has been multiplied by lambda of sigma, and some of those eigenvalues, a lambda sigma, will be smaller than one, some will be greater than one. Remember that these lambdas are L to some power, so they have to be positive. Okay, and so they could be small, they could be less than one or greater than one. So if the lambda and sigma is greater than one, then that direction, as it were, in eigenvector space, that direction grows. And if it's less than one, then that direction shrinks. And so what we can do a little bit more formally is we can order the eigenvalues. And technically we would order that their magnitude. So we'd say modulus of lambda 1 is greater than or equal to the modulus of lambda 2 is greater than or equal to the modulus of lambda 3, so on and so forth. And so then what we can do is we have three cases to consider. So case one is lambda of sigma is greater than 1. That will mean that the L, remember lambda is L to the y, so that means that y sigma is greater than 0. And so that means that A of sigma prime is going to be greater than A of sigma, and so that grows as L increases. So the more coarse graining you do, that direction gets magnified in the eigenfunction the eigenvector expansion. So that's case one. Case two says, well, let's suppose that lambda of sigma is less than one. And if that's the case, that can only happen if y sigma is negative, so that exponent. So that means that A of sigma prime is going to be less than A of sigma. And so that means that this shrinks as L increases. And then there's a marginal case where lambda of sigma is equal to 1. And then that means that y sigma is equal to 0. And so A of sigma prime is equal to A of sigma. And so it doesn't change. Okay, now this case, the last case, I don't want to spend much time thinking about it. So this case is called the marginal case. And we're basically not going to be saying very much about it. The first case where they actually grow, that case, we're going to call that relevant. And the other case we're going to call irrelevant. Now, why do we use those terms? Well, think about what's going to happen now as we do many iterations. So we're going to be doing many iterations of our renormalization group transformation. We're going to be still doing those iterations. We're still going to be in the linear regime. So we're going to assume that we can do that. And then what's going to happen is only the components of delta K, which are larger than, well, yeah, which are larger than 0, survive. So basically, the relevant directions get amplified, and the irrelevant ones shrink. So let's think about what that means in terms of the critical manifold. So last time we introduced the critical manifold. And so let's suppose that we are not on the critical manifold. Then ultimately, the vector k under renormalization will flow away from it. So we can draw a picture of that. So let's draw a picture like this. So I'm going to draw the critical manifold in two different ways. So let's suppose I take a side view. I'm going to call this a side view. Okay, so here is our critical manifold in coupling constant space. Here, let's say, is our critical fixed point. Now we know that if you're on the critical manifold, that represents a critical system. And if I start off with coupling constants on the critical manifold, do renormalization group transformations, I will end up at the critical fixed point. So I know that the flows inside the critical manifold all flow into this like this. I'm just showing you sort of side view of it, but you can imagine. Now, let's suppose that I'm no longer on the critical manifold. So now what's going to happen? So let's suppose now I start over here. Well, we're going to figure that out, but let's first of all draw the eigen directions for this critical fixed point. So this critical fixed point will have some eigen directions which are irrelevant. They, as you do renormalization group transformations, they shrink. And so those components get smaller and smaller, and therefore you get closer and closer to the critical fixed point. Those, in fact, are the arrows that I've already drawn. If I'm starting at those arrows, I'm proceeding, I do renormalization group transformations, I am going in towards the critical fixed point. So my deviation away from the critical fixed point is getting smaller. So therefore, those are the irrelevant directions. So then the relevant directions I can sort of draw like that. So these are going to be this is going to be the relevant direction, and the in-plane ones are going to be irrelevant. And then if I were to start off the critical manifold at, say, this point over here, what do we think the flow is going to look like? Well, we know ultimately the flows from here are going to go outwards along the direction, which is the relevant direction. So here's the relevant direction. The flows are going away from the critical fixed point like that. So the only way that I can make this be a continuous flow diagram is if the trajectories sort of look something like this. So if I start on, on the critical manifold, I just flow in the critical manifold. If I start off slightly away from the critical manifold, then what I will do is I will flow initially inwards towards the critical fixed point, and then eventually, ultimately, those eigenvector directions are going to be too large. They're going to grow, and they'll push me away from the critical fixed point. And so that is our side view. And if I were to draw the sort of top view, so then what I have is a picture I drew for some of you the other day. Here's my critical fixed point, and then I have my flows coming in towards it like that. And then the ones that are off the critical fixed point, I can't really draw them. I'll screw it up if I do. So just imagine them coming down and then sort of coming out of the board perpendicular to the plane of the picture. So this thing here is the critical manifold. And this thing here is the critical manifold. That's our generalized picture. So now let's put this into perspective. So let me now draw for you an example of this. So this example is a real life example. This example is what you can calculate, and we will calculate it for the two-dimensional Ising model. So I'm going to sketch for you what that looks like for the two-dimensional Ising model. So what I'm going to draw are only two axes. Remember that the Ising model normally the one that we want to consider is the nearest neighbor Ising model. So in general, though, we would have next nearest neighbor, next nearest neighbor, next nearest neighbor, and so on and so forth, as we've talked about. And we know that these higher order interactions get generated by renormalization group, and we're going to construct that. So I'm just going to show you here K1, which is the nearest neighbor coupling. And K2, which is the next nearest neighbor coupling. Okay, so then I'm going to draw for you the following thing. So let's suppose that we just think about the Ising model. Okay, so you know so when we talk about K1, so this K1, this would be, for example, J. What? What happened? It's not updating on, why isn't it updating? Okay. Can somebody go online who's got and see if Zoom is still, if it's working on Zoom? Wow. Now what? Did any glitch happen? Like it was something flashed? It just stopped writing. I don't know what's going on. Okay, this is where we do the unplug. This is what?
It's just frozen.
That's really bad. Frozen since 108.
Yeah.
I'm not going to re-record this lecture. Okay.
That's true.
2 weeks ago.
Shoot.
I was like, oh, now it's back.
Great.
Okay, is it on Zoom?
Your Zoom meeting address.
Good question. Let me send it. Let me send it to you.
No, but no, I just type it in.
Yeah, I know, but you'll need the password, which of course I have no idea what it is. So I know what I'm going to do. I'm just going to do it like this. Okay, so I just want to, where's Apple so useless? Copy, right, copied, okay.
Okay, got it.
You got it?
Yep.
How?
It's not recorded yet. Yeah.
So the screen share is cancelled.
Yeah. You just, oh, no, it's still there.
Okay, so if I do this, do you see it on Zoom?
Yeah.
Okay. All right. Okay, and you can hear me, right?
Yeah.
Okay, fine. All right, so, what was I going to do? Oh yeah, if you had the nearest neighbor Ising model. So what would happen is you would say that's J over KT. So what should happen is this, you would think that if you have a high K, that means that you've got a small temperature, right? So then you would think that you're going to flow something like this. And then if you have a small K, that would correspond to having a high temperature. So this would be high temperature. And this would be low temperature over here. And so you would expect that the thing is going to flow like this. And you would say, here is the transition temperature. This is going to be J over KBTC. But this is just what we're calling KC, or K1C. Okay, so that's what you would expect. Okay, so this is just a picture without knowing anything about renormalization group. Okay, now let's think about this from the renormalization group point of view. So you could say, let's suppose I started with the next nearest neighbor Ising model. Okay, there's no nearest neighbor interactions at all. What you know is going to happen is that it's going to generate all other interactions. So it'll generate, if you start off with next nearest neighbor, it'll generate next nearest neighbor and so on. But it's also going to generate nearest neighbor interactions. Okay, I've got some nonlinear function of all the coupling constants. Initially, the nearest neighbor one is set equal to 0, but after I've done a renormalization group transformation, there's no reason for the nearest neighbor one to be 0. So what's going to happen is I'm going to get a flow diagram that looks something like this. There's going to be some critical fixed point in the middle here. And what's going to happen is there's going to be a critical manifold that goes like that. And in that critical manifold, if I look at the direction of the flows, they will flow in to this. So I start with the nearest neighbor Ising model. It will generate some K2. It will generate some nearest neighbor interactions. If I start off with just nearest neighbor interactions, I will then generate some nearest neighbor interactions. And so if I start off with no nearest neighbor interactions whatsoever, so that is equal to 0. Once I've done one RG transformation, my next nearest neighbor Ising model will now have some small component in the direction K1. It'll have some small component in the direction for the nearest neighbor. And my nearest neighbor one, if I start off away from there, I do a renormalization group transformation, even though the nearest neighbor one does not have any next nearest neighbor interactions, after renormalization, it will have developed some. And so its trajectory will go in the up direction like that. And the same thing can be true for all the different directions. Okay, but this is the critical manifold that I've just drawn for you. But we know that there actually have to be relevant directions. In fact, we know how many directions there have to be. There have to be 2. Why? Because think about what a relevant direction does. A relevant direction pushes you away from the critical manifold. It pushes you away from the critical fixed point. So if you want to actually put the system at a critical fixed point, you have to adjust a bunch of variables. Each variable that you have to adjust corresponds to one of the relevant directions. Okay, if I've got one relevant direction, it means I have to tune some variable to have a coefficient of 0 in my starting coupling constant vector in order that I flow into the critical fixed point. If I've got 2 relevant directions, then I have to adjust 2 things in the lab, say temperature and external magnetic field. I adjust those to special values so that then I don't ultimately flow away from the critical fixed point. So the number of relevant variables tells me how many parameters in the lab I have to adjust, tune the dials on my machine in such a way that I get to the critical point. So we know there's got to be two of them. So I'm only going to draw one of them here. So here's the relevant directions, and if I'm on those, then I flow away like that. So that's got to be the picture. And then I've got to join up all the dots. So I can join up all the dots sort of like this. And so on. So I can get the global flow diagram from knowing the fixed points and the local flows. So let's have a look at what those fixed points are. So you can see that here at the origin, a lot of these trajectories flow into this high temperature fixed point. This high temperature fixed point here, I've already called it high temperature. That high temperature fixed point describes the state of the system above the critical temperature. That describes the paramagnetic phase. So this actually is paramagnetic. And it's a phase. Well, how do we know that it's paramagnetic? We know it's paramagnetic because all the coupling constants have gone to zero. So that's just a paramagnet. On the other hand, if I'm looking at the phase, so all the spin-spin interactions have all gone to zero. So now I've just got individual spins interacting with an external magnetic field. That is a paramagnet. On the other hand, the low temperatures, all of these flows here are going to some low temperature fixed point, and that low temperature fixed point turns out to describe the ferromagnetic phase. So let's put this over here. Let's go to page 144. So what we've just learned from all of this, so some important take-home messages. So the first conclusion is that the relevant directions push you away, push the flows away from the critical fixed point. So if you want to actually get to criticality, you have to have in your initial coupling constant vector zero components in the relevant directions. And so what that means is that the number of relevant directions is telling you the number of variables you have to adjust in the lab to get the system to be critical. That's a very important thing. This tells you that these things actually have these relevant variables have a physical meaning. And notice that these relevant directions are associated with a particular fixed point. So if you might go to a seminar and you might hear some physicists say, oh yeah, this thing it's a relevant variable. Okay, saying something is a relevant variable is a meaningless statement. If you say something is a relevant variable at the Wilson-Fisher fixed point in the two-dimensional Ising model, that is meaningful. You have to say what fixed point it's relevant at. So there could be a variable that is irrelevant at the say one fixed point, but it is relevant at another. And you can see that over here on the left-hand side. So on the left-hand side, if you look at the direction, the relevant direction, so that this is relevant at the critical fixed point. So that's that purple curve. That relevant direction pushes you away from the critical fixed point. But that same direction is irrelevant for the paramagnetic fixed point. Look at the paramagnet, that flow goes into that. And so what happens is you have a picture of your coupling constant space where there can be multiple fixed points. Those different fixed points represent different phases of the system. So two, relevance, etc., is always associated to a particular fixed point. You have to say which fixed point you're talking about. And what that means is that something that is relevant at, for example, the critical fixed point might be irrelevant at, e.g., the paramagnetic fixed point. Okay, so that's that. And then what we've learned is that the phases of the system, meaning the phases of the system, its phase diagram, the phases of the system can be read off from the flows. So for example, at low temperature, this flow diagram that we've drawn says all the flows go to K1 equals K2 equals 0, and of course all the other Ks as well. And so, and what that means is then, that means that there is no spin-spin couplings. So if you're in the basin of attraction of the paramagnetic fixed point, all flows will go towards the same fixed point. I mean high T. Thank you. Yes. Yeah. Thanks. I meant small k, but high T, exactly. So there's no spin-spin coupling. So what that tells you is, even if you're 1 millikelvin below TC, so you're over here, if you look on the left, so just where I'm drawing my pen on the left, I'm very close to the critical fixed point, but on the left-hand side of it, okay? Then after renormalization group transformations, many of them, I will flow into the paramagnetic fixed point. All of those systems to the left of that fixed point are in the basin of attraction of the paramagnetic fixed point, just like we saw before last lecture when we looked at the dynamical system. So even if you're 1 millikelvin below the critical temperature, you will behave as if you're being dominated by the critical, the fixed point at high temperature, the paramagnetic fixed point, and you will flow there. So you read off the phase diagram of your physics system, not by calculating in the same way that you would do normally, but just by looking at the renormalization group flows. The renormalization group flows tell you the phase diagram of the system. Okay, and okay, so that's that. Okay, what else did I want to tell you? Okay, that's it. Okay, so now what this tells us is that these flow diagrams then tell us the origin of universality. So it tells us the origin of universality is the following. Both in my picture over here, both the nearest neighbor Ising model and the Ising the nearest neighbor Ising and the next nearest neighbor Ising, regardless of where I start, they will flow in towards the critical fixed point, and then they will flow away from it along the critical fixed point relevant directions. And those relevant directions are a property of the critical fixed point, not of my initial system. So those critical those critical directions, these are properties of the critical fixed point and not the starting physical system. So we can predict then that the nearest neighbor Ising model and the next nearest neighbor Ising model will have a temperature dependence of, say, heat capacity and whatever as a function of T minus Tc, and it will be the same critical exponents because they're all controlled by the same relevant directions at the same critical fixed point. So that is the origin of the behavior. Okay, let me just say a word about the phases of the system. So as we said before, the phases can be read off. So the phases of the system are the sinks. So so for example, so there's the K1 equals K2 is equal to 0. That corresponds to either J going to 0 or T going to infinity. And in either of those cases, those correspond to a paramagnet. So let's just remind ourselves why. So if the case of J going to 0, so that is a paramagnet with no spin-spin interactions. That's what I said before. That's the natural way to think about it, but it's not the only way to think about it. So I could think about it as T going to infinity. So if I think of this as being T goes to infinity, then I can think of this as being a system where the entropic fluctuations are more important than energetics. And at the heart of this statement is to remind you that, remember, the free energy, the Helmholtz free energy, is the internal energy minus T times the entropy. So as I go to high temperatures, it's the entropy that dominates over the energies. And so we can think of this in either way. Similarly, if we look at what happens at the K1, K2 are going to infinity. So now what's happening is, so J over KT has gone to infinity. So I can think of this as either, this can happen in one of two ways. One way that this can happen is that J is going to infinity. And so therefore I have got a huge spin fluctuations, spin interactions, I should say. And so that tends to order the system. Or another way of saying it is that T is going to 0, and so the energetics dominate over the entropic fluctuations. And so this renormalization group picture of how to do statistical mechanics and think about the phase diagram of the system is completely consistent with your intuition that you've had up to now from thinking about just regular thermodynamics, but the interpretation is the same, but the mechanism is now based in this dynamical system picture of what the system is doing. So we've talked about the number of relevant variables being the number of physical variables. So a corollary of all of this is particularly of point number 1. Is that when I have these y's, so there should be one y variable associated with, say, little t, and one variable associated with the external magnetic field H. So we can call this y sub t and y sub H. And those are the two variables that you have to tune to be at a critical point. Because remember, at a critical point, our phase diagram looks like this. Here is H, here is T. Then my phase diagram looks like this. There's a line of discontinuities, and then there is the critical temperature Tc, and that critical temperature Tc is at H is equal to 0. So I have to tune H to 0 and T to Tc in order to get the critical fix point. And then here's something which I'm not going to dwell on. We know that this direction here, this is a second order or continuous phase transition. And earlier on, we talked about what happens as I go from here to here. So this is spins all pointing up. This is all spins pointing down. And so the magnetization is discontinuous as I go from low temperatures, change the magnetic field from negative to positive. So this ferromagnetic phase has a discontinuity. This is a first order phase transition. And the renormalization group fixed point associated to the ferromagnetic phase is a so-called discontinuity fixed point. And it has some very specific values for these things. For example, it turns out that one of the critical exponents, one of the y's, has to equal the spatial dimension of the system. Okay, and I don't think I'm going to go into that. So this gives you that, for example, y sub h is equal to d. I'm doing this from memory. I think it's true. I'm not going to look it up. But anyway, we're not going to go into that. Okay, so that's the picture of the renormalization group. So what is it? So let me just let's just recap the logic here. So essentially the logic that we are the logic that we've come up with then is that this RG picture has derived the assumptions that are made ad hoc by Kadanov's block spins. So let's just very quickly imagine, as an example, a system where we have, say, one relevant variable. And we can think of that variable as being temperature. Okay, so then we've got a coupling constant, which is basically just temperature. So we can say that our RG transformation is T prime, is some transformation that gives, starting with the initial variables of the system. And so that's my renormalization group transformation. Then I write down a fixed point. So the fixed point is T star is RL of T star. And then I linearize. So then I get that T prime minus T star is equal to RL of T minus RL of T star. And so that then is equal to just lambda L, the IG eigenvalue, times T minus T star, okay? Because RL of T star is equal to T star, and plus higher order terms. So then I can say that my eigenvalue, lambda L, is equal to the derivative of this function, drl by dt, evaluated at the fixed point value T star. And I know from the semigroup property I know that lambda L is equal to L to the y sub t for some exponent yt. And so therefore, so now if I use this equation, this one over here, then so if initially at some temperature greater than Tc, so then I define T to be T minus T star over T star, then T prime will scale like T, L to the y sub t. And if I do n iterations, then I will get the Casanov picture. Then I can iterate this. And so if I iterate that n times, then what I get is that T after n iterations is equal to T times L to the y sub t to the nth power. If I look at how does the correlation length scale, so that starts off as being a function of t, and then after n iterations, it's grown by a factor n, L to the n times psi of the nth iterate t of n. And so that tells me that psi of t is equal to L to the n times psi of t L to the n y sub t. And I'm going to choose my L to the n, some sneaky value, so some number divided by t, all raised to the power 1 over y sub t, where b equals some number. Why do I put this b in there? Well, L to the n should be an integer. So choose a value B so that L to the n is an integer. That's all. And then that says, if I do that, then psi of t is equal to b to the minus 1 times t to the power minus 1 over y sub t times psi of b. So, and that's happening as t goes to 0. Okay, so that's our picture. Okay, so why is this great? Well, you're thinking, well, this is like what we did with Kazanoff's block spins before. So B is equal to some number chosen. So L to the n is some integer. Okay, and what we've seen then is like psi of t goes like the correlation length at B. So this is far away from little t equals 0 or t equals tc. So that's generally going to be a number of order angstroms. And then this is going as t to the power minus 1 over y sub t. And so that implies that the critical exponent nu is equal to 1 over y sub t. So everything there is just like what we saw with the Kazanov block spin construction. But there's a huge, huge difference between what I just showed you, what I raced through, because we've seen it all before with Kazanov, and what we did when we first saw this. That huge difference is that we know how to calculate And how do we know that? Well, because we just have to find the eigenvalues of a matrix. We've got our renormalization group transformation. Here it's just a simple function, but in general it would be a matrix. I just have to find what its eigenvalues are. I know from my semigroup property that those eigenvalues have to be of the form L to the y sub t. So when I go and find those eigenvalues, then I can find the exponent y sub t by just taking those eigenvalues and taking the logarithm and dividing by L. So I know how to calculate y sub t. I didn't know it before, but this time we know how to calculate it. And the reason we know how to calculate it is it becomes from solving the linear RG matrix eigenvalue problem. So if I know what those matrices, what those eigenvalues look like, I know that those are, for on general grounds, they have to be L to the y sub sigma. And so that means that y sub sigma is equal to the logarithm of lambda of sigma divided by the logarithm of L. And so I can calculate those exponents. And that's the amazing thing. Now, the other thing is psi b here is far away from t equals 0, t equals tc. And so that means it's basically going to be small, say a few angstroms. And it's going to be in a regime away from critical, but perturbation theory works. So perturbation theory works. I can just do any calculation I want to calculate that, and that's how we can calculate everything. Okay, so one last thing I want to do before we finish. So we can do the same thing for the. I did this for the correlation function. We could also ask, how does the free energy density scale? So let's just do it again in the same simple example. We can also calculate the RG scaling of, say, the free energy per spin. So what we know is after one iteration, the free energy has gone down by a factor L to the minus D times F now as a function of T prime. So as before, I do n iterations. And then I get F of T is equal to T over B to the D over Y sub T, F of B. So I've done n iterations and I choose L as before. If I differentiate to get the heat capacity, I differentiate with respect to T. So that tells me that the C goes as T to the minus alpha. And I can read off what that alpha is. Well, that means that D over Y sub T must equal 2 minus alpha. So the free energy scales as T to the D over Y sub T. So if the heat capacity scales as T to the minus alpha, then the scaling of the free energy is minus alpha plus 2. Because I do 2 derivatives of the free energy to get the heat capacity. So therefore, I know what Y sub T is. Y sub T, I just showed you, is equal to 1 over nu. And so what we've just derived is D nu is equal to 2 minus alpha. And this is Josephson scaling law. Now we saw that before, but now I know what nu is. Nu is calculated from Y sub T, and that means that I've just calculated the heat capacity experiment. And the same for all the other variables. And so what I've just shown you then is how it is that we go about using a renormalization group to give us all of the scaling behavior. Okay, so I'm going to stop there. It's 10 to 2. So next time, what we're going to do is we're going to take the two-dimensional Ising model, and now we're going to actually do the renormalization group transformation. So we're going to construct an approximation for how to compute the projection operator that does the coarse graining, and then we're going to actually do the calculation. And what we're going to do is we could calculate the critical exponents, but what I'm going to do is sort of go halfway. We know the exact critical exponents from Onsager. So what we can do is we can work out, if you know the exact critical exponents, what should be the renormalization group eigenvalues. And then I'm going to compute the renormalization group transformation and compute the eigenvalues and see how close they are to what the exact results would be. Okay, and that's what we'll do next time. Okay, so hopefully everything got recorded. I will stop the recording now, and